We're back. So let's continue. Let me share my screen. So now I guess we are already comfortable with the fact that we're having this sequence of rotations in order to get a final rotation about an arbitrary axis of this axis, arbitrary axis R, by a rotation of phi, by bringing this axis into aligning it with the z-axis and rotating it in that axis and returning it back. But the question is, why are we pre-multiplying and not post-multiplying? Why are we pre-multiplying? Any guess? Or will it even matter? Will it even matter? Well, what if, okay, I don't have an answer now. I don't have a definite answer. Regarding whether if we change the sequence of post multiplication, that means that here this matrix is the first rotation, and then this one goes in here, and then this goes in here, and then that goes in here, and then this goes in there. Okay, I don't have an answer now. Okay, I'll verify it and then confirm it with you in the next meeting, if whether the order, or whether we pre-multiply or we post-multiply, will have the same effect in terms of this computation of arbitrary rotation in an rotation in an arbitrary axis. My guess is that it doesn't matter, because the effect is like canceling of the rotation, but I have to verify it to make sure that it is a correct answer. Okay, but if that is the case, then if my answer is that it will have no effect, because we are rotating and then bringing it back to the same axis, then most likely that we say that when we do pre-multiplication, most likely it will have the same effect in terms of computing the rotation matrix, but I have to verify that. Okay, so now the question is, why are we pre-multiplying and not post-multiplying? That's the first question. The second question was, will it matter? That's the second question. I say, I'm not sure. I have to verify. Let me put that one as the things that I will have to answer for you next meeting. Any one of you? Why are we post-multiplying? Martin? Why are we pre-multiplying? Sorry, why are we pre-multiplying and not post-multiplying? Okay, so this is the question. So what if we say, let's assume that, okay, these Rx with respect to alpha negative is the first rotation. So what does it mean? For example, if that is the first rotation, so that means that the order here will change. So going, this is going here is negative, right? Going here is positive. Okay, going here is positive. Okay, so going up is negative. So if we go up first, no, it's not correct. No. So the answer is the order indeed will matter. You understand? Because here, okay, the order will matter because here, if we say, if we follow this and we say, okay, so we first rotate by negative alpha and not alpha. If this is the first rotation, we say by negative alpha, so negative alpha is going up like that. Okay, so that means we're going to rotate, well, maybe we rotate, maybe, or maybe it's the same. Maybe we'll just rotate it geometrically into a different axis. I mean, we rotate it geometrically, then we rotate it on the other side. Okay. Okay, I was just trying to make a conjecture of whether the result will be the same. But why are we pre-multiplying? Okay, if we say from our last discussion that we rotate with respect to the reference to the vector, to the reference frame that is stationary, then we say that in this case, when we rotate here on the negative, okay. Okay, this is negative alpha. This is x, right? See, rotation about x. Are you following? Yeah. So this is the first rotation. So we're rotating about x by negative alpha, by an alpha, not negative alpha. Okay, that's positive. So when you rotate by a positive alpha, what we are doing is that we are doing here. We're going into that first rotation, this one. Okay, so this is 1. So that means that our stationary axis is like the one that we mentioned before, that we rotate about the stationary axis. Here, we rotate from identity axis, from the identity into rotating with respect to the stationary axis. So this, we can say that this could be a reason that in this case we rotate with respect to the stationary axis. That means we can assign an identity matrix here. There is an identity matrix where you rotated with respect to the x, the stationary axis. Okay. The next. Next, what happened? We rotate about the y-axis. Where is the resulting axis here? When you rotate like that, what will be the resulting axis? Okay, where if this is x, so what will happen to y and to v and w? So the rotated axis will somehow becomes maybe here. It is your v and your w will be somewhere here. Okay. Yeah. But now are we rotating with respect to U, V, and W, the new rotation axis? We are not rotating with respect to that. Because if we rotate with respect to the new rotation axis, then we need to post-multiply. But we are not we are not doing that. We keep on rotating with respect to the stationary axis. So we rotate again with respect to the Y, this Y, which didn't move. So that's why we pre-multiply. Next, we multiply again to the Z axis. So whenever we rotate, this U, V, and W will change. But we never, on the next rotation, we don't rotate with respect to U, V, and W. We keep on rotating with respect to the stationary axis, X, Y, and Z. And so we keep on post-multiply. We keep on pre-multiplying. So we pre-multiply here, we pre-multiply here, and we pre-multiply. You understand? We don't rotate to the new axis. Any question? Tomi-san, look like your face is very confused. Tomi-san. Okay, my drawing here was gone, but in my drawing, there was, okay, there were 3 axes like that, and then another axis rotating somewhere like that, and then you rotate again like this, and you rotate again somewhere like that. So you keep on rotating, yeah? So you rotate here, you rotate here, you rotate here, okay? In that case, if you have R1, R2, R3, so you rotate with respect to the new frame. So you have R1 times R2 times R3. Okay? But in our case, you keep on rotating with respect to this frame. We keep on rotating to here. It doesn't matter where is the new frame, where did the new frame go, but we keep on rotating with respect to the X, Y, and Z frame. Okay? So in that case, that's why we always pre-multiply. We don't do this, but we keep on doing here. Our rotation is you rotate based on this stationary frame. Okay? Any questions? Tomi-san.
I don't have questions, sir.
Did you understand?
I think so, sir.
Okay, what is the question? Why you don't think so? I mean, when you say you think so, that means that half of it, you don't think so.
I kind of understand, sir. I think I'll need more time to look at it.
Okay, just for now, okay, the rule of thumb or the way to understand it is that if you keep on rotating with respect to the same axis, the stationary axis X, Y, and Z. In this case, we keep on rotating always with respect to the X, with respect to the Y, with respect to the Z, X, Y, and Z, like that. Yeah, they don't change in terms of the new axis, so you pre-multiply. Okay, the first rotation, then the next rotation, you multiply it before it. The next rotation, you multiply it before it. The next rotation, you multiply it before it. The next rotation, you do again. Okay, it is different from this sequence of rotations where you rotate here and then you rotate based on this new axis. You rotate based on the new axis. You rotate based on new axis. In this case, you keep on rotating. You keep on pre-multiplying. You keep on multiplying post-multiplying. You multiply here, you multiply there. If there's another one that you rotate again here, you multiply again here. Post-multiply. But if you keep on rotating about the stationary axis X, Y, and Z, it doesn't matter where is the new resulting axis, then that one will be pre-multiplication. If you have R0 here, maybe R0 with respect to, maybe it's with respect to the X. Okay, then another rotation are maybe -1 with respect to the Y. Okay, then you post multiply it. Okay, then maybe another rotation with respect to Z. We call it -2, rotation -2 about the Z axis. Okay, again you pre-multiply because this is about, this rotation is with respect to the stationary frame. Okay, okay, I hope that's clear. Let's continue. Okay, I still have remaining 30 minutes to do the transformation matrix. So now, so this one is understood. Okay, what is this now? Okay, so now we can combine. This is just an Euler, this is a convention of what kind of rotation. We don't need to discuss that now. So we can combine, now we are ready to combine the rotation as well as position changes. So we call it a transformation matrix where you have the rotational part and the position part. So that means that, for example, if this frame rotates and move here, so it rotates and travel there, is like an airplane that rotates, you know, and travel there. We can determine its rotation as well as its change in position. So we have to consider that all those movements are independent of each other. That means we can separate them. Okay, so if the plane rotates and changes orientation and moves into position at the same time, we can, in our basis of computation, we can isolate the rotation alone. That means we can rotate the plane alone here. So maybe if the plane was flying initially in this position, and then suddenly here, it becomes like that. Okay, the nose is here, and the nose is there. Okay, that means that we can isolate the rotation. That means we can rotate here already with that nose. The nose is here, and then afterwards we move it in position to there. Okay, because those movements are independent of each other. Okay, just like position of X, Y, and Z. Okay, if you have movement of X, Y, and Z at the same time, but you can isolate movement of X alone, isolate movement of Y alone, isolate of movement of Z alone, and then you can combine them later, and the result will be the same. Okay, so the same thing here. So the good thing about the transformation matrix is now you're not dealing rotation and position separately. You are dealing them at the same time. Okay, so now instead of a rotation separate, position separate, you have a transformation matrix A where the rotation and the position are together. Okay, so now how do you do this? How do you do those you know, when you transform, you move from one frame, rotate that frame, you move for another frame like that, and you move in another frame again. How do you do that? Well, it's the same thing. You post multiply those transformation matrices. So maybe if you have frame 1 into frame 2 into frame 3, for example, if you have transformation of frame 1 with respect to frame 2, then from frame 2 with respect to frame 3, then you can get the total transformation of frame 1 with respect to frame 3 with respect to frame 1. Okay, the same thing as how we post multiplied the rotation matrices. Okay, but we have to consider that now the inverse of the transformation matrix is not equal to its transpose, not anymore. Okay, but if you want to consider to compute the inverse of the transformation matrix, this is now the inverse. The inverse is the inverse of this is that you inverse the rotation matrix, which is the transpose, and then here you inverse again the negative of the inverse of this. You inverse this, okay, you inverse that, the negative of that multiplied by the inverse, then multiplied by the position, the same position vector. Okay, that's all. Okay, the post multiplication and the pre-multiplication applies the same way as the rotation matrix. That's how I want to emphasize. Okay, so now here, for example, if you have several rotations from 0, this one rotation, this frame to that frame until the Z frame. So that means that until the nth frame, so you have a transformation matrix. The first transformation matrix multiplied from 0 to 1, this one, 0 to 1, and then 1 to 2, this one. So this is 0 to 1 transformation. Okay, it moves to there. Another transformation from 1 to 2, another transformation from I minus 1, I minus 1a to I, and so on until to the nth frame, I or n minus 1 frame. Okay, so keep on multiplying, because in that case you post multiply, because you transform, you rotate, you transform based on the new reference frame. So you transform until A0, E1 until you get a total transformation. Well, we can call it also 0 from 0 to n, or in our convention here, 0 to A to the n. Okay, so that's clear. It's just the same. That's why we spend a lot of time to show you the transformation matrix, pre-multiplication and post-multiplication, because that is the foundation for this. So now, you can see how this chain of reference frames will lead us towards a robot now. That we will attach several reference frames in the robot, and then these reference frames we can post multiply in order to get the end-effector movement. So in this case here, this is like the base of the robot, and these are the joints of the robot. Now this is the hand. So all we need to do is post multiply all those matrices in order to know what is the position and orientation of the hand with respect to the base. Okay, so there is that vector. Eventually there is this vector, that movement. Okay, there is that position vector from 0 to the end-effector defined by that, and also there is that rotation from 0 to the end, where to the end of the robot, where this is 0 and 1, which defines the position and orientation of the hand of the robot with respect to the base. That's all. That's the main purpose for us to discuss all those positions and rotations, transformation, in order for us to determine how does the hand of the robot move with respect to its base. Now, the next discussion will be in the next meeting. How do we assign a convention, so that we will discuss Hartenberg convention, so that we can just use the rotation and position as it is, as what we discussed. So if you can lay the foundation in that Hartenberg convention to define the transformation matrix, and then that's it, we're done. We'll use exactly the same computations that we discussed before. Okay, so for example, in this case, if this was a planar robot, we discussed mostly about planar, because we don't want to discuss about the Hartenberg convention for now. We say that the position vector, this position, will be defined by this. Okay, for now, the position vector is this. Okay, so the z-axis is here. Z-axis is 0 all the time. So here is 0. Okay, 0, it doesn't move in terms of the z. And then here, this is, remember, this is the position that we are trying to do, the x and the y position, which is what? A1 times cosine, there, A1 times cosine of the first A1 times the cosine of the first joint angle, and then A1, I mean A2 plus this one, A2, so that one plus that one, A2 times the cosine of 1, 2, that means 1 plus 2, yeah? So this is cosine of theta 1 plus theta 2. Okay? Okay, to say the same thing as here, we discussed this one extensively before. So now this is the rotation. What is this? This is the rotation, the basic rotation with respect to the z-axis. Okay, there are two basic rotations. So you rotate in this z-axis here about theta 1. Okay, theta 1. Then you rotate here about theta 2. So that means that's the result of rotation about the z-axis with respect to theta 1. Theta 1 multiplied by another rotation about the z-axis about theta 2. You understand? Okay, if you compute that, you will get this. So what is this? What is this kind of rotation? So rotation about the z-axis, it will be 0, 0, 1. And then here, cosine of theta 1, cosine of theta 1. Here will be sine of theta 1. I think that's minus sine. That's correct. And then 0, 0, 1 there. And then the next will be, that's this one. And then the next, you copy the same thing. So cosine of 2 now, sine of 2 minus sine of 2, cosine of 2, then 0, 0, 1. Okay. You multiply them together, check if you'll get this. Okay. So now this is our first attempt in the planar robot to combine the position, which is this position, and the orientation of position vector and the orientation matrix into one matrix of transformation matrix. Okay, so that's I think that's the end of our discussion. Any questions before you think you'll be ready for test 1, long test 1, before our long test? So everything from the start until now, until the transformation matrix where we combine the position and orientation into one matrix so that we can transform with respect to from one frame up to how many frames that you are transforming. So that's the generality of the transformation matrix. It doesn't matter as long as you keep on, you post multiply according to the sequence of rotations or transformations. It could be transformations because it is both position and orientation at the same time. So now, instead of drawing, if you draw yourself like this geometrically, your eyes will be all strained already. You still commit mistake. But if you're dealing with all transformation matrices, then it's easy for you to compute. Okay. Any questions? Please answer the exercise that I gave you independently, or if you want, you work with your classmates. But I would recommend that for you to, even if you do with group work with your classmates, please try to again work on it by yourself independently for you to prepare in the long test 1. So long test 1 lab, please submit it earlier for you so that you don't need to worry about submission on Friday. Maybe you can submit it on Thursday. Okay. Any questions? Any concerns for the long test? Okay, so everyone will be there in the lab, the lab session in the environmental science lab. Please wear your mask. If you have face shield, please bring your face shield as well. Okay? So we'll maintain social distancing, and Camela will be there, and maybe I will also call Caloso. Okay? Okay, if there are no questions, then I'll see you when? This Friday. Yeah, Friday afternoon during long test 1, during our lab time. Okay, thank you. And I stop sharing. And let me check attendance. Smile. Are you sure, Mr. Musa, you're not maintaining social distance?
Sir.
Yes. Musa,
Sir.
Yes.
This boy. Sir, this boy was speaking. I have a problem with my mic. That is why I'm attending here.
Okay. Okay. I thought you were Musa. You, Musa and Boao, you look similar. Are your mother?
They are
sir.
brothers, sir.
No, Musa is also here, sir.
Huh?
Sir, Musa is also here.
Yes, I
Musa
know.
is also here.
Okay, that's fine. But please, you're very close there. Very close to each other. Okay. So anyway, I mean the proximity is very close. Be careful. Do you have vaccines already? No. Okay.
No,
Yeah,
sir,
anyway.
I have cousins.
Okay, that's fine. But make sure next time you wear your masks and face shield to protect yourself.
Yes,
Okay.
sir.
So never mind on the test. If you don't wear a mask, I won't let you in. Okay. You know it already. Okay. Okay. Good luck. Study very hard, and see you Friday afternoon, 2 o'clock during lab time.
Thank you, sir.
Okay. Thank you. Bye.